So today we will discuss about the propositions, few propositions when we say it's a convex or concave. Okay, so that's important. Properties we have finished, and we'll see some propositions of it. Okay, so we will talk about propositions. Right? Proposition is that reserve convexity of a set. Correct. So few propositions are there for us, so we need to discuss them. So first proposition is okay. First proposition is the interaction. Proposition is the intersection wait, I will put something below. I am unable to write it smoothly. The intersection that's UI that belongs to I. Okay, is the big I, and this convex set Ci of any collection that is Ci I belongs to I of convex that is. What does it mean? It means what is intersection mean? That is the multiplication. Actually, when we say interaction in the sets, intersection means, for example, intersection of A set plus intersection of B set. Correct? So it is in the same context. Intersection of I sets means different sets. The intersection of different convex sets is a convex. What I have written is a set is a no, of convex set is set no is set convex set convex set is convex. I have to written what I have is wrong here. Here it is convex. Okay. Means if we multiply different convex sets, okay, so that is here, but I have written here different. If we multiply different convex sets here, and we see here that intersection of different convex sets is convex itself. Okay, that's the first proposition, which is important. Okay, the intersection, as you know, we see in the sets, for example, in the probability also, probability of A intersection B, like that we see. So in the sets also, like for example, two sets, we see intersection of set A versus set B. And for example, we have set 1, 2, 3, set A, 3, 4, 5, set B. Then intersection will be equal to 1, 2, 3, 4, 5. Okay. So the multiplication, the intersection of two convex sets will be convex. So remember that is the first proposition that is here. Then second proposition is the vector sum of C1 convex set 1 plus C2 convex set 2. Okay, I will just erase it. It is not necessary. No, this thing already. C2, the vector sum of C1 plus C2 of two convex sets C1 and C2 is convex. That's another proposition. If we sum two convex sets, the final set will be the final set also will be the convex set. Okay, same like the intersection. If we multiply two convex sets, it will be convex, and if we sum two convex sets, it should be also convex. Okay? Then third one, the set x plus lambda c is convex or any set or any convex set the set x plus lambda c is convex for any convex set c, vector x and scalar vector x and scalar lambda. And further more, if C is convex set, if C is convex set, correct? If C is convex set and scalar lambda 1, lambda 2 are positive, then what we have? Then we have what? Okay, so you understand what I am writing. First one is like in intersection, second one is summation. Okay, that will be this. Third one is if we there are three things actually. One is set, one is vector x, and one is scalar lambda. So where there is multiplication as well as summation in this. So it is saying x plus lambda c will be also the convex set. Further, if C is a convex set and scalar, there are two scalars, lambda 1, lambda 2, are the scalars, positive scalars, then what we will have, for example, we will have lambda 1 plus lambda 2 C, it will be equal to directly the multiplication, okay? Lambda 1 C plus lambda 2 C. correct? So that will be the convex also, correct? No problem in it. Then let us go for the next proposition. The fourth proposition says the interior this one I have the closure and the interior of a convex that is convex, right? The closure and the interior means the inside the set and the inside the boundary of the convex set, interior as well as closure, that will be also treated as convex, right? The last proposition we have, the image and the inverse image of a convex set under an affine function in a given function or convex. That's the next proposition, and that's all about the propositions. Okay, so the image and the inverse image of the convex set under an affine function is the given function will be also convex, right? There's no problem in that. Okay, so only 5 propositions we have. We have intersection, we have summation, and we have when we multiply or when we have convex set with the multiplier and the scalar and vector. That time also the function will be treated as convex set. Closure and interior. Closure and interior means like this: when we have a graph, for example, it is under the boundary of this function. So this is the boundary and closure and interior. Interior will be treated as like this. Interior of the convex set is convex. Okay, the image and the inverse image of the convex under finite affine function. Affine function, given function are also treated as convex only. Okay. No problem in that. If you have any doubt, just let me know. No? We have another slide. Any doubt regarding this? So we will do a small graphical representation and we will wind up this topic completely. Convex sets, okay? Because we have done the definitions and propositions of convex now. It should be very clear to you. So graphically, if I show you, it should be very clear to you now. For example, I will make the graph like this. So graphically, this is called convex. When for example, the definition of convex, when the tangent is below the graph, and this is called, which I have told you in the beginning of the class, this will be treated as concave function. This is the opposite. If it is, for example, f of x, then it will be minus f of x. This will be treated as concave function. Okay, so at least if you have any difficulty in understanding by definitions, at least by graphically remember what is convex function and what is concave function. Okay. Leave definitions, you need to remember the propositions, but at least visually what is convex and what is concave, it should be very clear. Here we have two concepts as we have already discussed. One is convex, one is strict convex. Okay, one is concave, where strict convex is when, can anyone tell? When strict convex is when x is not equal to y. Okay, so that time we say for all x and y that belong to convex set, x should not be equal to y. Okay, that time will that function, then that set will be treated as convex set. Then what is the next interpretation? This convex set will tell us, the convex set will tell us about the minimum of a function. That's why we are learning it here. That's why we are discussing minimum of a function or global minimum. Correct. Then concave set will what will how it will be like interpreted? It will be maximum of a function or can be also global maximum. That that interpretation I have given you already. When we will call it local, and when we will call it global. Fine. Then slides are over. I'll write add more slides here. Then in the last class, we wrote some function like this. When we wrote f ax plus 1 minus a y is less than or equal to a function of x plus 1 minus a function of y. That time this function will be called as convex. This is a convex function. And where we have x, y that belong to C, the convex set, and A ranges from 0 to 1. Correct? Fine. So we also learned this function. This function is called concave. The function is called concave if minus f is convex. So remember this point also. We learned in the last class. Correct? Did we learn or not? Then we also learned the function f is called strictly convex. Strictly convex if the above inequality, right, is strict strict for all x y that belong to C, with which we discussed 2 minutes before, with x should not be equal to y. Correct? And all a that ranges from 0 to 1. Correct? That's all. These are the important points you need to remember. When a function, the reverse of a convex function is concave, the function is called strictly convex when we x and y are wait for me. When x and y that belong to any convex set, when and only when x is not equal to y, that time it will be called the strictly convex. Fine. That much is enough for it, or you need any more clarity? So we can draw a little graph here. We can draw graphical representation, for example, here. No. For example, I will draw the graph here. Correct? And I will make one curve here, which will be in the functional form. Okay. Correct? Then I will one line, one point is this, then one end point is here. Should be actually parallel. Treat it as a parallel. Okay. Here it is the end. These points are end points. Okay. These points are end points. Then if we draw a line in between this graph, if we draw the line, for example, like this, then this will be the convex line, or then this function will be treated as convex function, okay? Because the line is within the graph, okay, not outside the graph. That's important. It's like this, and wait 1 minute. Somebody's calling it. Okay, we make graph like this, and then this will be treated as the convex function. Okay, then I will write it here as a f of x plus 1 minus a f of y. Treat this as endpoint, okay? It should be endpoint. This will not count this much. Two endpoints and one line between the graph, which should be within the graph, not outside the graph. So we have, that is the point to remember. The lines, the point, the line we draw here should be within the graph. If it goes outside the graph, then we will not call it the convex function. Okay, so uh, this function, like this, is the illustration of the definition of the function that is convex over a convex set. Okay, this is the illustration, graphical representation of the definition of a function, convex function, that is convex over a convex set. C. Okay, so we have we have functional form a into f of x plus a minus 1 minus a f of y. Okay, so these things are, that's all about the this. So we can write this function f of y, or here we can write it f of, for example, f of z, y and x we have above, we'll write it f of z. Okay, so that's all about the total story of convex sets. No need to worry about it, anything. That's all. Okay, any doubt? Any question? I will wind up this topic here only. So I will not go ahead because this much information is enough for you. You don't need much information than this. As like, that's not like, I actually teach more than what you need every time, because it's not, don't need extra information is also sometimes not useful, because it will confuse you. So remember this much only. That's enough about the convex. This is more than enough what I have taught you about the convex sets, convex properties. What was that? Properties of convex and concave functions in this context. In what context? In optimization context. Okay, that is the topic in the syllabus. You can see properties of convex and concave functions in the context of optimization. So in the optimization context, we know that convex and concave functions, their definition form, their functional form, and their graphical representation. Everything is, and when we treat a function as a convex function, when we treat a function as a concave function, that we know it very well. And when the function is not a convex or concave function, that also you should know by now. Feasible point, feasible set, that also I have cleared already. Then let us go to the next topic. The next topic is interpretation of the Lagrangian multiplier. Correct? Interpretation of the Lagrangian multiplier. So how do we interpret the Lagrangian multiplier? That is this. If I say it's the rate of change, that's enough. I will wind up, but that will not be enough for you to understand. Okay, it's a rate of change. The Lagrangian multiplier is a rate of change. Actually, it's a rate of change. First, we will write about this. What is it? Lagrange multiplier. Nothing new in it, as we have already done the things in it. We have solved the functions, we have solved the questions in it. We have seen the minimum and maximum in Lagrangian multiplier. We have seen the maximum and minimum in the classical optimization. So maximum and minimum in the classical optimization, and we have seen the necessary and sufficient condition in both classical optimization as well as Lagrangian optimization. Both things, everything we have seen. So it is completely associated with that only, but I will write it with the functional form. Suppose we have a function, it is one and the same thing. Okay, don't get confused, but I have to define something with respect to this. That's why I am doing this. For example, we have we have a function f, where r and that ranges to r, some real number. So there will be some optimization problem. We will because Lagrangian multiplier we use only when we have optimization problem with respect to constants. So we know it, minimize or maximize some function. Okay, so what we do minimize f of x, correct, subject to what, h of x when it is equal to 0, that is equality constant, where I ranges from 1 m, correct. Then inequality constant, for example, g of I of x is less than or equal to 0. Here it is not I, it is j, because I we have already given above. Where j ranges from 1 to n m or p, whatever you want to write. So we have two forms of optimizations. One is equality, one is inequality, which you know it very well. Then what is the definition of Lagrangian multiplier? If we have, for example, more than till now we have learned only two variables, only x, only one Lagrangian multiplier. Now we will define it with respect to more than one Lagrangian multiplier. For example, what is the definition? So the definition for that will be definition of Lagrangian. The Lagrangian function L. Let's write it here. I will put it here. L, that R, where we have three parameters n plus m plus r, which n and r here, okay? Where we have basic function, or objective function, then constant functions m and r, and where like this Lagrangian function will be the part, that will be the part of the Lagrangian function. Or it is defined as, just remember, it is defined as L. L will be the Lagrangian symbol. X is the basic variable or that function. The lambda will be one multiplier, and then mu. Why two? Because it is equality as well as inequality we are including in the definition. Then it will be function of x plus no, it is not. Summation of m, where it ranges from 1 to m Fine. Lambda times I into h times I of x correct plus same equation with where j ranges from 1 to r. Okay, we have given j here, r here. Okay, r I 1 to m. It is inequality part. First one is equality part, second one is inequality part. Mu j g j of x. That's all. The functional form of the Lagrangian multiplier when we include both equality as well as inequality constants. So that will be written as this. By definition, it will be written as this. Correct? No problem in it. Then, okay, this part will be called the equality constant part. Equality constant part, okay? And this part will be treated as inequality. Inequality constant. Correct? Any doubt? Because you see here we have two where h of x and h of x with respect to the functional form f of x. When it is associated with h of x, that time it will be treated as a like when we minimize f of x with respect to h of x, that time it will be treated as equality constant function, composite function, but with equality constant. When we minimize f of x with respect to g of x, g of x, okay, that time it will be treated as inequality constant function. Combining both, when we solve a function, when we have both equality and inequality problem, constants, equality and inequality constants, when we are solving any function f of x with respect to equality as well as inequality constant, then that function will both things will be included in one function. And that's why in the first part here you can see lambda and mu has come. Lambda will be equality one and it will be inequality one. Mu will be inequality one, inequality multiplier. Lambda will be equality one. Correct? No doubt in it. Are you guys listening me or not really? My mic is on, no? Yeah, it is on. Fine. Then what are these parameters? So we will see the parameters. What are these parameters? Where we have three parameters here. One is lambda, one is mu, and one is x. X is the variable. Okay, variable function variable. So what we will write here, f of x is, it is objective function. Objective function. Correct. Then we have lambda and we have mu. Correct. So we will see what is lambda. Lambda will be, it will be the combination of 1 to m lambda. 1 to m lambda means what? Different. 1 to m lambda means what? Lambda 1, lambda 2. It is not. Lambda 2, lambda 3, lambda 1 to m means lambda m, right? It means this, it is the vector, hmm, vector of Lagrange multiplier. Remember it, it is very important. Lagrange is the vector of Lagrange multiplier, correct? Multipliers with respect to our corresponding to the equality constant. That is important here. Equality constants, right? We can write the vector this way as well as we can we give some t when we write it the vector form, we give the rest for t also. So it is not what is it? It is the lambda is summation of, or it's a range from 1 to m lambdas. That makes the vector of Lagrangian multiplier, which are the part, which are the when that lambda will be treated, what that lambda will be treated, it will be treated as a equality constant, correct? Then we have mu also. Mu ranges from j to r. How we will write that? We'll write mu equals to u1, mu2, mu3, for example, till mu r, correct? It's also a vector. We'll put a t here denoting it. Is a vector of Lagrange multiplier. Corresponding to the inequality constant, okay? Corresponding to the inequality constant or constants. That's all about it. By definition, it is this, what we call equality and what we call inequality Lagrangian multiplier. So inequality part will be 1. When we combine both the functional form, the composite functional form will be like this. When we combine both, when we combine both inequality as well as equality constant functions. Okay, so till now what we had done, only the equality constant, because that's only in the syllabus. Okay, so but for to make you better understand, I thought to include both the things together for a better use in your future. Otherwise, in the syllabus you can see there is the Lagrangian multiplier method, necessary substitution is optimized subject to equality constant only. Inequality is not mentioned here, but we need to at least mention it. What is inequality constants? In future, in the coming chapters, I don't know whether we will touch it or not. Okay. So That's why I am just giving you the idea of inequality constant. Inequality, like then there will be hard and soft constant. You, as you know it earlier already, hard and soft constants with respect to some gradients. Hmm? Gradients with respect to some gradients, we will have hard and soft constants. Correct? So this is the composite function, the functional form of objective function and constant function. When we have both ways of constant function, that is equality and inequality constant functions, that time we will write the the combination of all the things together. Objective function plus equality constant plus inequality constant, we will write like this. So this will be the composite function. So we have two multipliers here, one is lambda, one is mu. Lambda is equality constant, equality multiplier, okay, and mu is inequality multiplier. Both will be treated as multipliers. Both are multipliers, okay, correct? No, and both are Lagrangian multipliers only. Now the question is, what is the my question to you is what, how, like your question should also be this, and my question is also this. What is the function of multiplier? Correct? What is the function of multiplier? Hmm? So that is one of the important thing. What is the function of multiplier? So can anyone tell what is the function of multiplier? What is the role? What is the function of multiplier? But how we will, if I define, if I tell you, define the multiplier. Multiplier, what, when we have two multiple. Till now it is okay. This, the equality and inequality topic is over. Okay. Because I, that was in the middle of the topic, so that's why I discussed it here. Now the thing is, what is the role of multiplier? What is the role of that lambda? That thing I am discussing now. Okay, till now this is over. This part is over. Till here, this is convex sets are over, completely over. Lagrangian multiplier. What is the functional form of Lagrangian multiplier with respect to equality and inequality constants? Equality, we have done many examples. Inequality, you don't need it in now. If we get the time in future, we'll solve some equations with respect to inequality constants. Okay. Or or even both. No problem in it. But the thing is, but the thing is, what is till now it's over, okay, completely. This is the functional form, composite function, when we have two multipliers, lambda and mu, equality constant and inequality constant, and we have one variable, functional objective function or variable, that's x. We want to maximize or minimize x with respect to some constants. Okay, then we can have function like any function, cost function we want to minimize, profit function we want to maximize. So every time we will have some of the other function. And remember, remember in economics, to solve any function there are always some constants. To solve any function, every time there are constants. So this is very important with respect to economics or real world actually, because economics deals mainly with the current problems of the economics. So for example, I am teaching you, what is your constant now? You are unable to come to university, that is the constant. You are not able to come here, you are not able to attend the class offline, that is the constant now. Economics, when we talk about economics, any cost function, profit function, investment function, huh, trade function, anything, anywhere, there will be some constants. We have to solve the function with respect to some constants. Wait, excuse me for 1 minute, I will receive. हाँ जी बोलो बोलो अभी चल रहा है थोड़ी 10-15 मिनट और चलेगा हाँ 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 ठीक है कब से भी जाएंगे क्या हम्म हाँ 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 ओके फाइन बिल्कुल भी खराब नहीं है क्या हो गया अरे क्लास ले रहा हूँ क्लास ले रहा हूँ madam was calling. Fine. So we have these parameters here. So the next question is, my next question is, what is the role? Till now it's over. I guess it should be very clear to you now, because we have already solved constant equality constant functions, and I may give some assignment on the basis of equality constant functions only, where you need to, I will give you the instructions what you need to calculate equality, like you need to calculate maybe equality constant function, and minimum and maximum, and necessary and sufficient conditions, the equality constants. That thing I will give. Inequality constant, we have not solved any problem, but the functional form I have shown you, it should be very clear by now. How does it work? Hmm? Now, my only question is, here is this symbol, lambda. Somebody's mic is on, please switch it off. Correct. Thank you. There is this lambda. So what is the role, and what is the, how you will define the lambda? What is lambda? So the question is, what is lambda? Which lambda? Multiplier, okay? Not only the Lagrangian multiplier. Lagrangian multiplier. And if we write like this function, when we write x and lambda and u, that time this is Lagrangian. This will denote, which I have written already, but I forgot to describe it here. I have written, you can see here, L. So this will be called as Lagrangian symbol to denote the Lagrangian like function. So how do we define the lambda? For example, with respect to anything, any function, with respect to any function, how do we define lambda? Anyone? First, I will give the students chance to students. Then I will tell my what I have to see you. Anyone? What is the definition of lambda? I will give the short definition today. Tomorrow we will solve some problem with respect to this lambda. Okay. Already time is over, but I have to go to department also. So madam was calling. Otherwise, I thought to take long class. For example, we have a function f. We have a function. Okay, f prime, f star, or f prime c. Then that is lambda times lambda star c. What is lambda? Lambda star. What is lambda star? The derived value. It is the derived value. Okay. When derived, when we have three functions, when we differentiate any composite function with respect to x, okay, then put f prime x equal to 0, f prime y equal to 0, then f prime lambda equal to 0. The value of lambda which we get here, lambda will be equal to some, not 0, lambda will be equal to some number, okay? So that time it will be treated as we put as the derived value of some function n or c, correct? Usually the lambda, this will be how we will define it. I will just give the definition. Tomorrow we will see some more details about lambda, because this is also important. Tomorrow we will see some more details about lambda. If this is the case, for example, if this is the case, then lambda will be defined as lambda will be defined as the value of the Lagrangian multiplier or Lagrange multiplier. Lagrange multiplier at a solution problem solution of the problem. It is the solution, no, right? Correct? As the solution of the problem is equal to, then remember, is equal to the rate of change, the rate of change in the maximum, in the maximum value of what? Of the objective function. So what is so at different points the definition may change, but remember, overall, what is lambda? It will give us the rate of change of, because when we solve the function with respect to x, y, and lambda, so we have to substitute those values in the original function. Okay, which original function? The objective function. Okay, we have to substitute those values in the objective function and get the final value of the objective function. Then what is the role of lambda there? Lambda will tell us when x changes by 1 unit. Lambda will tell us how many units the output will change. Correct? So lambda will tell us the rate of change in the maximum value of the objective function. At what rate the objective function will change with the unit change in what? With the unit change in lambda. Correct? Somebody please switch off your mic. Okay. So this is the definition of lambda. The rate of change, sometimes the definition, because with respect to some function, its definition is this. So it is the, actually when we say the derivation, what is derivation? Derivation is also the rate of change. Okay, the derivation is also the rate of change. Remember, so this lambda will tell us how how much one variable changes with respect to that lambda. The lambda means what? The value which is given by lambda. Okay, for example, the value given by lambda is, for example, I will write here, the lambda given by value is 1.5. Lambda is 1.5. So if x changes by 1, the output will change by this much unit. Lambda will tell us that. If x changes by this much, output will increase by this much, 1.5. Okay, that is the role of lambda. Tomorrow we'll do some functions. Tomorrow we'll do some solution